So I'm going to give kind of a survey talk of some recent new directions to do with cylindrical algebraic decomposition. So two new directions in particular, about various adaptions of CAD motivated by the computational logic community, and about the use of machine learning to improve CAD implementations. But before I talk about them, I will give a few slides defining what CAD is, for those who don't know, and trying to motivate why you might care about it. Okay, so let's start with the definition. So a cylindrical algebraic decomposition, or CAD for short, was introduced first by Collins in the 1970s, along with an algorithm to produce it. So let's define the three words here. So a decomposition, we mean exactly what you think we mean by that word, splitting a space into cells such that the union of the cells is the whole space and that the cells don't overlap. Sorry, I've missed, my empty set hasn't come through on the slide there. Apologies, first typo on slide 1, so the intersections should be empty. And we're thinking about decomposing Rn. So these cells are going to be semi-algebraic, although in the definition we just use the word algebraic, which means they're described by polynomial sign constraints. And the real meaty property here is the cylindrical word. So what does this mean? So it means by definition that the projection of any two cells in the decomposition onto a lower coordinate space with respect to the variable ordering. If you do those projections, you either get an identical cell or completely disjoint cells, but not overlapping ones. So what this really means is that the cells in my decomposition are all stacking up like plates in cylinders over cells from a decomposition of the coordinate space of one dimension smaller. And the semi-algebraic descriptions that I mentioned make that explicit. So for example, if X was the first variable in the ordering, the semi-algebraic description would have a condition just on X, which would be the projection of the cell onto X, and so on. So these CADs are usually built relative to a set of polynomials, such that each polynomial has constant sign in each cell. So in any given cell, a polynomial is either positive throughout the whole cell, or 0 or negative. This property is called sign invariance, and that's what Collins' original algorithm produced. Of course, from such a mathematical object, you can uncover all kinds of properties of the polynomials. It has the power of making an examination over infinite space possible by only examining a finite set of sample points. You can just pick one point from each cell, and if you look at all of those sample points, you'll know what's happening for the polynomials everywhere. So ideally, what we really want, this is a workshop on constraints, so what we really want is a CAD built relative not to polynomials themselves, but to sets of polynomial sign constraints, so that each constraint has constant truth value, true or false, in each cell. So this will be called truth invariance. So sign invariance for the polynomials in the constraints implies truth invariance, but it's possible to achieve truth invariance in more efficient ways as well. And of course, if we have a truth invariant CAD, we can uncover all kinds of information about our constraints, including descriptions of their solutions from the semi-algebraic descriptions of the cells upon which the constraints are satisfied. So here's just a pictorial representation of that. It's a very simple CAD in the plane relative to the polynomial defining the unit circle. And my CAD consists of 13 cells here that I'm cycling through, coloring them in red as we go. So each cell has a semi-algebraic definition on the left hand of the screen. Some of the cells are 2-dimensional, some are 1-dimensional, and some are 0-dimensional. And what we see here is the cylindricity property. So if we look, say, in the middle, there's like a cylinder there in the middle that's being split into 5 separate cells, such that the polynomial has constant sign on each cell. So the sign of the polynomial here is 0, so that has to be a different cell to either side of that. Okay. So this is just a pictorial representation of a CAD, but CAD is a computed in computer algebra system, and it's stored as information involving polynomials. So that's just a representation of what's happening. What the algorithm's actually working with are sets of polynomials organized in a tree-like structure. So we think of the decomposition as a tree branching by the restrictions on each variable. So this is all dependent on an ordering of the variables. So the example that I've been giving here assumed we're decomposing with respect to x first, and then for these different choices of x, we have sub choices for y. Okay, so what's the motivation for producing a CAD? Well, the original and still probably most important motivation is quantifier elimination in the reals. So the real QE problem is where you're given a formula where the atoms are polynomial constraints and it contains quantifiers, and you want to produce an equivalent formula which doesn't contain quantifiers. This is possible, proven in the 1930s by Tarski, and CAD offers one route to do this. So for example, does there exist x such that x squared plus 1 is less than or equal to 0? Oh, that should be for all x. I'm sorry, that's my second typo there. Is it true that for all x? The answer is false. Is it true there exists an x? The answer is true. It becomes a bit more interesting when you have variables that are not quantified. So in this third example here, does there exist x such that x squared plus bx plus 1 is less than or equal to 0? So b is a second unknown here, but it's not a quantified unknown. So what is the answer to that? Well, it depends on b. For some values of b, there will exist such an x, and for some values of b, there won't exist such an x. So the output is a formula in b. And this formula is equivalent to the input. That is to say, if this formula, the output is true, then the input is true. If the output is false, then the input is false. So how is it I produce something like that with CAD? So just continuing with the same example, suppose I want to study the problem, there exists x such that x squared plus bx plus 1 is less than or equal to 0. Well, I'll take the polynomial that's involved here, x squared plus bx plus 1. Here's a plot of its graph, where x is the vertical axis, b is the horizontal axis. I know that's not the standard notation, but that's because I want to project down onto b, and I like projections to go down vertically. So I've made x the vertical axis there. So I will build a sign invariant CAD relative to this polynomial, and we get some cells. So I've colored in my full dimensional cells blue and yellow just to show where the cells differ. But to be clear, there's also some one-dimensional cells, such as this line segment that my mouse is moving along here, and then also some zero-dimensional cells. The point there is a cell in its own right. So the black circles here are the sample points from the cells. So once I've got my CAD, I can then check one sample point from each of my cells and see if this is satisfied or not. And I've colored them in here, red where it's not satisfied, green where it is satisfied. So I've tagged them true or false. And then I can project down the true cells and find which regions of the b-axis the true cells project onto, which is which values of the b there does exist such an x. And we get the answer that we saw before, although split into 4 cells, but of course we can squeeze them back together with less than or equals and greater than or equals. So I just showed you an example there of existential quantifier elimination by CAD. Just to be clear, you can also do universal quantifier elimination. You simply convert the logical formula into an existential one and then apply the same process that I just showed. So QE and CAD is kind of a classical area found in computer algebra systems. There are implementations in the big ones, Maple and Mathematica. In fact, at least 2 or 3 different implementations in Maple. There's a very good one also in Reduce. And there's some standalone systems for it, such as QEPCAD. And more recently, as I'll talk about in a moment, there's implementations in a variety of SMT solvers. So QE has applications throughout science and engineering. All kinds of problems can be boiled down to a quantifier elimination problem. A few examples here, automated theorem proving, loop parallelization, but also examples not even in the sciences, or at least not in the engineering sciences. Economics have been making use of QE in some of their analysis recently. And CAD does have applications independent of QE. For example, there's been some work in chemical reaction networks recently, identifying multi-stationarity. Is that a question? I'm sorry, I heard something, but I couldn't make it out. No, okay. All right, okay, so CAD, yes, it can be used for QE, and it has some applications. I'm not going to go through the details of how it works, but just in a sentence or two, basically we use polynomial projection operations to uncover key geometric information, and then we make use of real root isolation on those polynomials to form the decomposition. And the key trick is the substitution of sample points into multivariate polynomials to make them univariate, that allows us to just repeatedly use univariate root isolation. And the clever bit is that we make sure that's a valid thing to do, because the projection captures the key information about where cell boundaries would need to be to ensure that the generalization is valid, so that we can work at a sample point and know that we're representing a whole cell because we've ensured the cell boundaries exist at the point where that generalization would not be valid. So it's a nice algorithm, but it has one nasty sting in the tail, which is that it's very expensive. So by the end of this projection phase, this tracking of the geometric information, you end up basically with a doubly exponential number of polynomials, and even worse, those polynomials have doubly exponential degree. This is doubly exponential in the number of projections, i.e. the number of variables that you're dealing with. So also that means that as an upper bound, there's a doubly exponential number of real roots and a doubly exponential number of cells. So the best paper to understand this complexity is this one I put on the screen. Okay, so nice algorithm, but very expensive. So there's been some interesting work in recent years looking at adaptations and optimizations of this. I'm going to look at two particular new directions now. So the first one, I'm just going to define a slightly different problem that we want to solve before I introduce it. So the problem here is the problem that's called in the computational logic community the satisfiability of nonlinear real arithmetic, or NRA. So this means to evaluate this quantified expression here as either true or false, and it will evaluate to either true or false because every variable in the expression is quantified, and more than that, they're all existentially quantified. And this community tend to call the answer sat if it's true, and unsat, unsatisfiable, if it's false. So when they deal with nonlinear real arithmetic, F becomes a formula in Boolean logic, so atoms with ands, ors, and nots, and those atoms in the nonlinear real arithmetic are sign constraints on nonlinear multivariate polynomials with integer coefficients. But I just want to stress here that satisfiability is studied in all kinds of different arithmetics or logics. This is just one, NRA is just one that I'm interested in today. They also usually assume that F is in conjunctive normal form. So this problem is a sub-problem of real QE. It's basically real quantifier elimination where all the quantifiers are existential and every variable is quantified. And so in theory, it can be solved by CAD, but we've already noticed CAD is expensive, and also this problem has a lower theoretical complexity than the QE problem. This should only be a singly exponential problem to solve. So yes, we could build a sign invariant CAD for the polynomials that are involved in the formula, and that would allow us to solve this problem. But it's expensive, and it's expensive because it encodes a lot more information than we really need here. So a sign invariant CAD for the polynomials is a CAD that could study any quantifier elimination or satisfiability problem that involves those polynomials. It ignores the logical structure, basically. It only cares about the algebra and it ignores all of the logic. So a key question is how to adapt CAD so that it takes note of the logic and makes savings accordingly. Now, there's been lots of work on that over the years. I haven't got time to go through it all today, but I'm going to talk about the most recent and I think most promising route, which is the SMT approach. So the SMT approach to satisfiability problems is to basically separate out the logic from the rest of the mathematics that's involved. And then they use SAT solvers, which are excellent, well-developed pieces of software to explore the logic and have the SAT solvers suggest solutions to the logic. But those solutions may or may not be valid for the mathematical domain that you're working in. So then you need some kind of specialist software for your domain to check if they're valid or not. And that's called a theory solver. The theory solver is no longer dealing with logic. It's simply testing if a set of assignments, in our case, sign constraints on polynomials, can be satisfied at once. There's no logical structure for it to deal with. So this approach is called satisfiability modulo theories. Yet another typo there. It shouldn't be module. It should. So why is this a good approach? Well, it allows you to take advantage of SAT solvers, which are a really incredible piece of technology. So this slide, borrowed from my friend Vijay Ganesh, shows how many clauses in a logical formula a leading SAT solver is able to tackle. And you see that from the turn of the century, went from 1,000 clauses, and in 2015 it was well over 1,000, and this is now 6 years out of date. It's well over 10,000 now. So these have been astonishingly successful, and we want to take advantage of their success for studying our logic. So the schematic for how these SMT solvers work tends to look a bit like this. You have your input formula, and then you perform what's called the Boolean abstraction, which basically means you take your atoms, which for us are polynomial sign constraints, and you replace them by Boolean variables to form a SAT problem in Boolean logic, called the Boolean skeleton. Let the SAT solver study it. It will hopefully propose a solution. And that solution will say these variables have to be true, these ones have to be false, and that defines some polynomial constraints for us. And then we want to try and see if those polynomial constraints can be satisfied or not. If they can, we've got a solution to our problem. If they can't, we need to rule out that solution and hopefully lots of other solutions that are similar to it by generating a new clause to feed into the SAT solver. And this goes around in a loop till hopefully you find a solution, or if there is no solution to your problem, eventually you'll generate enough clauses that means the SAT solver cannot propose any new solutions to the logic, and the SAT solver will tell you it's unsat. So, okay, let's just take a step back then. We're trying to solve satisfiability for polynomial sign constraints. So the obvious connection between what I said at the start and what I'm saying now is try and use CAD as a SMT theory solver. So can we do that? Well, we can, but for it to be efficient, we need a CAD implementation that supports some non-standard functionality. We really need an implementation that's incremental according to the constraints under study. So the SAT solver gradually modifies its solution, so it may bring in an additional polynomial requirement to us. So we want to be able to refine our CAD, chop the cells down as we get additional requirements without restarting the whole computation again. We also might want the ability to remove polynomials, which would mean merging cells back together in order to maintain the most efficient CAD we can. And we also need explanations. So when our CAD says that a problem is false, so every cell says we can't satisfy this, we want to identify a minimal subset of the polynomial constraints that can't be satisfied together. So a good paper explaining how to adapt CAD for this is the one on the screen here by Kremer and Abraham. But you might be wondering at this point, well, you just told me that CAD is very inefficient. Why is a SAT solver plus CAD any better than CAD alone? So the key thing to understand here is that with the SMT, the SAT solver is commonly only addressing a small subset of the total constraints at once. So the logical structure may have a lot of ors in it, and so the SAT solver is proposing some assignments that together satisfy the logical structure, but because there's ors in it, it's only going to be a subset of the total number of constraints under study. And so the CAD that you end up building is a smaller CAD, because it's a CAD for less polynomials. So is this a good approach? Well, I mean, that paper reports that that it's pretty good. Certainly it's much faster than CAD alone, because we end up terminating early when there's a satisfying witness in the SAT case. And even in the unsat case, it can be faster because we can reach the conclusion of unsatisfiability by studying multiple smaller problems rather than one big problem. But especially in that unsat case, it still may be that you need to compute some very large decompositions. So we really want to adapt CAD a bit more to this situation. So I'm going to describe an approach now, and it's kind of inspired by SAT solvers. So I haven't got time to explain the history of SAT solvers, but the key algorithmic process going on in SAT solvers is making guesses, seeing what the implications of those guesses are, and when those guesses turn out to be wrong, as they often will, trying to derive a logical explanation that doesn't just rule out that guess, but rules out lots and lots of similar guesses. And that's the algorithm that's made SAT solvers so great. So we're trying to recreate that in our CAD algorithms. But to be clear, these algorithms I'm going to talk about now aren't actually CAD. They're kind of inspired by CAD and involve a lot of the technology of CAD, but they're actually producing something a bit different. So let's talk about the first one. This is a work from 2012 by Jovanovic and Demora, which presented an algorithm that they called NLSAT. And this was actually an alternative to the SMT framework. They call their alternative framework MCSAT. And this doesn't really separate out the SAT solver from the theory solver. So what does it do? Well, you build what they call models, which are the guesses, the educated guesses about what a solution might be. You build these models in tandem in the Boolean variables and the variables of your polynomials, the algebraic variables. And when you get a conflict in the Boolean variables, then you use the normal SAT solver approach to generalizing that conflict. And when you get a conflict with your algebraic variables, when some polynomial sign constraints can't be satisfied at the same time, then what they do is to build a single cell from a CAD, not a whole CAD, but a single CAD cell, which is the cell that contains the current model point, upon which the polynomials involved in the conflict are sign invariant. And the semi-algebraic description of that cell becomes the learnt clause, which informs the future search. So this was quite a revolutionary algorithm. It doesn't require full CADs. It uses less projection because we're only projecting the polynomials involved in the conflict, not all of the polynomials under study. It involves a lot less real root isolation because we're only building a single cell, not all the cells. And there's been other optimizations found since about how to make that single cell even more efficiently, such as the one by Brown. So we are building cells, but we're not building CADs. So what can we say about these cells? Well, the first thing to note is that these cells are produced independently of each other. They don't really talk to each other, which means that when we conclude unsat, what we have are actually cells that don't form a decomposition. They could be overlapping. So we call this a covering. So it's still the case that all of the space is covered by cells, but now the intersection need not be empty. Now this may sound like more work, but it's actually less work. It means you can have a smaller number of bigger cells to cover the space rather than a smaller number of, rather than a larger number of smaller cells, which take more work to produce. Also, the cells they're cylindrical in the sense that the semi-algebraic descriptions allow for the trivial projection, but they're not globally cylindrical. So these cells don't stack up in cylinders like the CAD cells. So this NLSAT algorithm outperforms the SAT plus CAD SMT approach, but it is a different framework. So it's not easily combined with other SMT modules. So I said at the start, I wanted to emphasize that SMT is a framework for studying all kinds of different mathematics, not just nonlinear polynomial systems. And this NLSAT doesn't kind of plug and play with the SMT solvers for problems in multiple theories in the way they would like. So a couple of years ago, me and my colleagues set to try and produce a covering-based algorithm that did fit into the SMT framework. And it was published earlier this year in JLAMP. And it's joint work with Erica Abraham, James Davenport, and Gerian Kremer. So it's an algorithm for deciding whether a set of polynomial sign constraints are consistent, i.e. can be satisfied at the same time. It has some similarities to NLSAT in that it builds coverings of spaces, not decompositions. And it's also conflict driven. So we allow our search to be guided by our past guesses to more profitable future guesses. But it's also different to NLSAT because it can be used plugged into a traditional SMT solver, and we maintain the cylindricity property. So we haven't lost that. We keep that property, and we also have our guidance in our search as part of the algebraic procedure. So it's not something that we have to encapsulate and then feed back to the SAT solver. It's something we actually do with the algebra. So this is just a very basic, the very rough sketch of the base idea. The paper has the technical algorithms. So the idea is this: we pick, when I say pick, I mean randomly guess a sample for our first variable, and then we keep making guesses to extend that sample through the dimensions in reference to the constraints that we have. And if that works, then great, we've solved the problem with SAT, but probably at some point our guess will mean that we cannot satisfy one of the constraints. So when that happens, what do we do? Well, we search outside in that dimension, outside the places where the constraints cannot be satisfied. And if the entire dimension doesn't contain a point that satisfies the constraints, then we're in a conflict situation, and we use CAD projection to rule out a larger area in the dimension below, larger than just the single guess point that we made, using the theory of CAD sign invariance. And we only conclude unsat when we've covered the entire bottom dimension. So it's basically a depth-first search through the search space where we're constantly ruling out as larger a region as we can to inform the future search. So I did attempt to make some slides to show this, and then I realized that my colleague Gerian had made some slides for a talk he gave, so I thank him. I'm going to use those slides for the next example. So here's an example of the approach. We've got three constraints here. It's all in X and Y, so just a nice simple 2D example. So the three constraints, the unsatisfiable areas add a layer of shading. So the satisfiable areas are here where it's white on the left and at the top right. And in the shaded areas, it's not satisfiable. So how does the algorithm work? Well, we start by making a guess for X. We pick X equals 0. As we can see, that guess is not going to be good, but we'll see how we're informed of that. So we look at X equals 0. These polynomials now become univariate. So we can do some simple univariate analysis, and we see that they each rule out a portion of the y-axis. And the key thing to note here is that we only need 2 of these dotted lines to fully cover the y-axis. So we can be informed, we can inform our future search using only 2 of the polynomials. We don't need all of them, so we can make a saving here. Now we have a choice. Now in my next slide, I'm going to pick C1 and C3 as the polynomials I use, but I could have picked C1 and C2 instead. And then I use CAD projection to generalize x equals 0, and it basically tells me you've got to go smaller than -2 or bigger than 3, which of course places me into the potentially satisfying regions where I want to be. So my conflict informed me to go in the right direction. I was a bit lucky here though. If I'd have picked C1 and C2, which would have been another acceptable choice, then you see here that the intersections are a bit further closer to the origin, and it would have just told me to go left of that intersection point or right of that intersection point. So it may have taken me another round of work before I find myself in the satisfying region. So there are some, there is a degree of choice, which can be lucky or unlucky here as well. But either way, we are getting pushed in the right direction by the algorithm. Okay, and then you would make a new guess for x, and wherever you pick your x, you'll then be able to extend it to a y sample that satisfies. So in that paper that I referred to, we had some experimental results on an implementation of this algorithm in the SMT rat system. It showed that this algorithm was much more efficient as an SMT theory solver than incremental CAD. It didn't outperform the NLSAT implementation, but interestingly, there were substantial example subsets where the algorithms outperformed each other. So there were 555 problems where our algorithm timed out but NLSAT completed, but also 358 problems where NLSAT timed out and our algorithm completed. So the algorithms are clearly different, and there's perhaps potential for some kind of meta solver here. What's not published yet, there's a paper under review, is a new implementation in CVC5, which does outperform not only the NLSAT in CVC5, but also all of the winning solver from last year's SMT competition, which was also based on NLSAT. So a few simple optimizations has pushed this beyond NLSAT. Okay, so I'm going to skip these slides for time. I'm just going to give this last slide on this topic, which is that this is still very much a work in progress. So I'm involved in a project at Coventry, also joint with the University of Bath, funded by the UK EPSRC, called DUCAD, pushing back the doubly exponential wall of cylindrical algebraic decomposition. And we're trying to implement a lot of these algorithms in Maple to try and allow for meaningful comparison between them, and then some future theory development and applications work on them. Could one of the organizers tell me how much time I have left, so I know how much to say on this next section? I think I've not got much, right?
Yeah, I mean, in 5 minutes, we're supposed to go to the next speaker. So you may want to finish in a couple of minutes.
Okay, I'll say just a couple of words. So the other direction that I could have talked about today, but I won't, was the use of machine learning to optimize CAD. So I already gave some hints about choices in CAD. So one classic example is the variable ordering. So here, there's a 3-cell CAD, exactly the same polynomial 59-cell CAD, depends if you pick Y first or X first. So this is just an example of one choice. And we've been looking at the use of machine learning to make these choices. And I'll summarize right to the end and say that machine learning does much better than any of the human-defined heuristics for this problem. But there's still a lot of work to do to further improve it. And I also like to make just kind of a general note here for anyone who's listening, that there's nothing particularly special about CAD in this respect. CAD has choices like the variable ordering, which don't affect the correctness of the output, but do affect efficiency. And there are many other algorithms in geometry and computer algebra that also you can make that statement for. And at the moment in our computer algebra systems, most of these choices are either taken by the user or perhaps by the developer. But in general, it seems machine learning could do a lot better, at least in a lot of the choices we've looked at. But a key question here is how to get the data to do our machine learning. So in algebra and geometry, we don't have the kind of data sets large enough to perform the deep learning that would really be the optimal way to do this problem. So the machine learning experiments that I didn't have time to describe, we're doing kind of classical machine learning algorithms, deep learning remains out of reach because of this data problem. Now, of course, we can randomly generate polynomials, but there are key questions about how to do that in a meaningful way. And we have a PhD student at Coventry working on this right now. So this is my final slide, and I'm going to finish with an advert that there is a fully funded PhD position available at Coventry. It's to work on the topic of machine learning to improve symbolic integration and symbolic simplification routines, co-sponsored by the software company MapleSoft, who make the Maple computer algebra system. So if you're interested in that, or you know a potential student who might be interested in that, I would be very grateful if you could let them know about it. These slides that I've gone through today will be on my website, and the deadline to apply is in September for a PhD to start in January. So if you have a student who's interested in computer algebra, geometry, but also machine learning, please let them know. And that's it. I can take any questions you have.